and the possibility is high currently. Try to come to class. If you are actually out because you're actually sick, get better first, okay? I will record it so that you can get caught up later. But if you're just home because you're contact traced, come to class at 11:05 or 11:10, stay caught up. It's a lot easier to stay caught up than to get caught up, right? So that's what's going to happen for the foreseeable future. Let me quickly review what we know. We started off talking about temperature, and we learned how to convert temperatures from Fahrenheit to Celsius to Kelvin, right? Kelvin's the best way to measure temperature because temperature is related to the kinetic energy. And so 0 temperature should mean 0 kinetic energy, okay? So that's why we use the absolute scale. The second thing we talked about is, well, sometimes you want to change the temperature of a substance. And how much heat it takes to change the temperature was given by m times c times delta T. So if microwaving water causes the temperature to change, how much heat you need is equal to the mass of the water times its capacity times the amount the temperature changes, right? You guys remember that? Is that your toolbox? Okay, and this thing here, the heat capacity, we look up in a table, right? We just look it up. We don't ever memorize it, although I think most of you know it for water, right? All right. So the thing we talked about on Friday was the fact that power is the rate that energy is transferred, okay? And so that is Q over T when we're talking about the thermal context. So on the warm-up, question number 1 was the temperature conversion. Everybody got it. Question number 2, you had to find the heat. Question number 3, you had to find out how long it would take the camp stove, right? And so if you're trying to find T, you cannot solve for things in denominators. So multiply both sides by T first. And then if you want to find the time, you can divide both sides by the power. So P equals Q over T. Another way to write that equation is that the time equals Q over P. So take Q divided by the P to find the power in seconds, okay? And that's as far as we've gotten. So today we're going to move on and talk about phase changes, okay? So if you're at home, don't listen to me. If you are here, close your computer. If you're at home, don't close your computer. Okay, if you're at home and you've got a question, you've got to unmute yourself and ask it, okay? Because I can't watch the little tiny chat bar on here all the time because I've got to switch to another screen for the presentation. So if you are here in the room, you just have to watch the screen. And if you feel like you're far away back there, feel free to move up. There's lots of empty tables. Okay. Okay, so we're going to talk about phase changes, all right? And we're going to start off. Do you guys remember the different phases of matter way back in 7th or 8th grade science? We talked about solids, liquids, and gases, okay? And there's actually 2 more phases that are kind of fun. There's plasmas, and there's Bose-Einstein condensates. So solid, liquids, and gases are normal states. We've seen them before. You've encountered them in 8th grade science. Plasmas are what happen when molecules get moving so fast that they fall apart. The atoms get stripped apart. The electrons get ripped off, the protons and the neutrons fly around, and it's just a big slurry of subatomic particles, okay? That is extremely hot, and it doesn't really occur on Earth except in very special circumstances in high-energy nuclear reactors where they're trying to make plasmas, okay? The other cool thing is a Bose-Einstein condensate, and this very rarely occurs also. It's what's called superfluidity. So if you take liquid helium and you cool it all the way down near to absolute 0, it becomes superfluid, and it can sneak between molecules and out the walls. You can't contain it. Okay, it's like magic. It passes through the walls of the container that it's in. It does cool stuff. But anyway, those are special ones. The ones we are going to focus on are the plasma and the Bose-Einstein condensate. I'm sorry. Those are the weird ones. Those are the ones we're not going to focus on. We're going to focus on solid, liquids, and gases. So let's quickly review what solids, liquids, and gases are. All right. So here's a little applet which will help us kind of visualize it. Okay, you guys see the applet there in the remote world? Garrett, you see it?
You can. Yes, you can see it.
All right, good deal. We can hear you. All right, so here is what things look like when you have a solid. When you have a solid, the atoms are connected to their neighbors. So here's kind of what happens, okay? Between all molecules, there's a weak attraction. So molecules like other molecules of the same type. It's called the van der Waals force. And so if objects are not moving very fast and they get near another molecule like them, they tend to stick to them, okay? So here you have a bunch of atoms, and if you look closely, you will notice these atoms are all in motion. They have kinetic energy. But if you look really closely at one of them, it doesn't move relative to its neighbors. This guy in the top corner pretty much stays in the top corner. He doesn't move around. Now, if we added some energy, these guys would be moving faster, right? Sooner or later, they will move fast enough that the little tiny weak attraction between them can't hold them together anymore. And that looks like this. Okay, that's a liquid. If you look really closely at a liquid, you'll notice that any one molecule can move around. So the guy that's over here might eventually, oh, there he goes. Trying to track him. He's moving through the fluid. There he is. So in a liquid, the exact same attraction is still there. But because they're moving faster, they can't get locked into their neighbor. They just kind of hover around their neighbor. They're still weakly attracted, okay? If this wasn't COVID and the whole class was here, we would go to the gym and we would play States of Matter theater, where you guys would all act like molecules. And you would move very slowly and line up with your friends. And then you'd move faster, so you'd just be a big blob, but you'd still be around the group. And then what happens if you move really fast? We get them lots of energy. Well, then they just fly around. Because they're moving so fast, when they run into one of their neighbors, they just collide and bounce off. And this is a gas. It fills the whole container. Every molecule can move pretty much anywhere at once. And they just collide into each other. But when they collide, they're moving so fast, they can't hook up. They just bounce off each other, okay? So solids, liquids, and gases are just about how fast or how much energy something has relative to the attraction between them, okay? That's kind of how solids, liquids, and gases work. Okay, so back to the presentation. I got to make sure I always share the right tab. So you should see the presentation again. Camden, can you see the presentation?
Yeah.
All righty. So here's what we know about solids. Okay, solids are generally a fixed volume and a fixed shape because the atoms can't move relative to their neighbors. So they have a fixed shape. Molecules are connected to their neighbors with pretty rigid bonds. You can think of them being connected by like little springs holding them together between the atoms. They can move, but they can't go anywhere else. They can just vibrate, okay? And there are many kinds of solids. The kinds of connections they have to their neighbors, you guys might remember from chemistry, have names. You could have molecular or covalent bonds. You could have ionic bonds. They can be metallic connections. They can be amorphous, but these are all solids, okay? And they are moving, but they don't move around. They just wiggle and jiggle, okay? Liquids, on the other hand, have a fixed volume because gravity tends to pull them down, but they don't have any fixed shape. They'll take the shape of the container because they can all move relative to each other. They still hang around together, but they are not locked in place, right? It's like freshmen in high school. You ever seen freshmen? They all move together. No freshman dares to go to the cafeteria alone, right? They wait until there's like 10 freshmen and they all walk down the hall together. It's for defense against those scary seniors, right? So they can move around each other, but none of them leave the pack. That's a liquid, okay? So some fun things. Molecules and liquids are attracted to each other, but they're moving fast enough they don't get locked into their neighbor. They just hang around their neighbor. So sand is an example of a solid which acts like a liquid. Sand can flow, right? If you got beach sand, it kind of acts like a liquid. So does corn. And you got to watch out. Since you live in Indiana, here's my little corn warning. Corn can act like a liquid, and you can drown in corn, okay? No corn molecule is locked into its neighbor, is it? No corn kernel. They move. And so one of the common ways people die in farming areas is what's called grain entrapment. You think it's kind of funny to go climb in a bin that's full of corn. But what happens when you get here? Well, the corn moves a little bit and you sink down and you can't get out because the corn acts like a liquid. But you are denser than the corn and you eventually sink down. And it's like quicksand. The more you struggle, the faster you sink. People routinely die of grain entrapment. So next time you see a big truck parked by the side of the road and you think it'd be fun to hop in there and swim around in the corn, just remember, it is the second leading cause of farm deaths in the Midwest. Grain entrapment. Because corn is like a liquid. Kind of pours like it, right? All right. That's a word of the wise. Gases. So gases generally don't have any fixed shape or size. The molecules are moving so fast, they don't connect to their neighbors. They just bounce around, okay? If they do collide with their neighbor, they collide elastically, which you guys might remember from our last unit, means they bounce off of each other, right? And they don't lose any energy. So we have solids, liquids, and gases. And when we transform from one state to another, we have names for those. So I think this slide looks pretty familiar to most of you. I think most of you know that when you go from a solid to a liquid, we call that melting. So you probably don't need to write this down, okay? But if you do, that's okay. These slides are linked online, so you can go back and get them later too if you need them. So think about ice. Ice is the solid form of water. When it turns into a liquid, we say it melts. If you go the other way, from a liquid to a solid, we say that it is freezing. Or, more generally, we say that is the fusion process. So fusion and freezing are the same thing. It's going from a liquid to a solid. When you go from a liquid to a gas, when you think about water, you might say it's boiling. In general, we say that is vaporization. Vaporization is going from a liquid to a gas. And when you go from a gas back to a liquid, we call that condensation. Okay? So you might get condensation on your mirror in the bathroom. Or if you have to wear a mask, you get condensation on your glasses, right? They fog up because of our masks. That is a gas, water in its gas form, turning into a liquid and forming little droplets, okay? Condensation. Now, there's a couple of special ones I don't have on here. Does anybody know what you call it if you go from a solid directly to a gas? Anybody remember that from chemistry? No, that's solid to gas. It's called sublimation. So dry ice, so at certain temperatures and pressures, some substances can go directly from a solid to a gas. And that's called sublimation. And if you go from a gas directly to a solid, that's called deposition. But you don't need to know that. That's just for fun. All right, so here's something kind of cool that happens. So I just want to show you a little video here. This is a beaker of water that is boiling on a hot plate. And it's kind of hard to see, but there's a little red line. This is a high speed. I did a fast forward on it. There's a little red line here. I don't know if you guys can see the temperature. Right here, it's climbing to near 100. Hey, there we go. Now the temperature's right at 100 and it's boiling. And over the next 5 minutes, it continues to boil. But the temperature doesn't change. Where's the energy going? If the hot plate is hot and adding energy to the water, and the temperature is not getting any higher, where is the energy going? Yeah, what do you notice about boiling water? It's got bubbles, and what do you see above the boiling water? Steam. What is the steam? It's the gas. So what happens when something boils isn't that the water keeps getting hotter and hotter, okay? If I were to keep going for another 10 or 15 minutes, eventually all that water would go away. But until it goes away, it'll never get hotter than 100 degrees Celsius, okay? When you microwave water, it heats up to 100 degrees Celsius. And if you keep microwaving, it doesn't get any hotter. It just starts going away. So when you add heat to water at its boiling point, the water doesn't get any hotter. The molecules don't move any faster. They just start escaping. They break the bonds that were holding them and they leave. Okay? That's the idea. So what happens when something boils is that the temperature doesn't change anymore. We have a conversion from a gas to a liquid. The same thing happens with ice. If you have water and it's at 0 degrees and you put an ice cube in it, or you put 10 ice cubes in it, it doesn't change it. It still stays 0 degrees. If you microwave a cup of water that has ice in it, it stays at 0 degrees and the ice just starts to melt. It doesn't get any warmer. It doesn't start warming up till the ice is completely melted, okay? So I'll try to show you a little visualization of that. So if things go well. All right, Austin, can you see the presentation there? Do you see a cup with a graph? All right, good deal. All right, so here's what happens. This is a cup of water, and it is a solid. It's an ice chunk. And there's little tiny molecules that you might be able to see in there. And I'm going to show you what happens when it converts to a liquid. So right now we are adding energy to this. And it's getting warmer and warmer. And now, right now, it's melting. So over here we have a graph that shows what's going on. And this is the graph that's going to be important. As it melts, we have less and less ice and more water, but the temperature didn't change. And now when all the ice is gone, the temperature will start going up again. So this is the graph that we're interested in. Here's what happened. When it was all ice, adding energy caused it to warm up until it got to the special critical temperature called 0 degrees. When it got to 0, as we continued to add energy, so look at this graph here. On the x-axis, we have the heat. On the y-axis, we have the temperature. So right here, we were adding heat and the temperature was going up. But when it got to 0 degrees, we continued to add heat, but the temperature didn't go up. The temperature stayed the same. It stayed at 0 the whole way. Is that a little hard to see? The temperature stayed at 0. And then when finally all of the water was melted, now it started getting warmer. The water started warming up. Okay? So let me show you that again. Keep your eye on the graph here. We're going to start with solid ice, and we're adding energy. We're adding energy, and the temperature is going up. Once we get to 0 degrees over here, now we're adding energy, but the temperature is not changing. Where's the energy going? It's converting solid to liquid. Now, when all the ice is gone, boop, now the temperature starts going up again. Okay? So temperatures do not change when we are changing phases. When we add heat and we're at the melting point, it changes ice into water. It doesn't make the molecules move any faster. Once all the molecules have been turned into water, liquid, instead of ice, then it starts adding energy and the temperature starts going up, okay? Same thing if we start with a liquid and we turn it into a gas. So here we're on a burner on a stove, okay? So right now the temperature is 50 degrees. If I start adding heat, the temperature goes up. And they'll keep moving faster and faster and faster until we get to 100 degrees. And when we get to 100 degrees, the molecules won't move any faster. The temperature won't go up. They'll just start turning into a gas. So here we go. We're at 97, 98, 99. And now you can see the temperature is not going up anymore, but some of the faster moving molecules are leaving. They're turned into a gas. So where's the energy going? It's going in to help the molecules escape. And eventually the water level goes down, down, down. When all the water is gone, if we could add more energy, the temperature would go up again. Okay? That sort of makes sense? There. Now the temperature could go up again if there was any water left, but it's all gone, so it's hard to make it go up. Okay? All right. So that's the idea. Let me stop that. All right, you should be back at the presentation now. Now, this is just a bonus. It turns out that even when water is not 100 degrees, sometimes it can evaporate, okay? And the reason that happens is sometimes an individual molecule gets enough energy to escape. Remember, these molecules are all banging around, smacking into each other, right? Every once in a while, even if you're at 30 degrees Celsius, a molecule will escape. So what happens to the temperature of the water that's left if one of the molecules gets enough energy to escape? Well, temperature is a measure of the average kinetic energy. And what happens if a molecule with a lot of energy leaves? What happens to the average? It decreases, right? I mean, think about it. If you had a prison and those really smart prisoners could escape, what would happen to the average IQ of the prison over time? It would go down as the smart ones escaped, right? If the fast-moving molecules escape, the average of what's left goes down. And so that causes the temperature to drop. So evaporation can happen at any temperature. So let me show you this. Let's suppose I have a liquid. I'm going to turn it into a gas. So even though I'm not at the boiling point, every once in a while, you'll see a molecule leave here because it happened to just get enough energy to leave. There goes one. Whoops. And now the average is a little less. So we say that evaporation is a cooling process. Evaporation causes the average temperature to drop. So a couple examples. Have you ever heard the phrase, a watched pot never boils? If you're going to watch a pot, you got to have the lid off, right? Unless you got one of those fancy glass lids. But if you have the lid off, then as the water gets warmer, some fast molecules escape and the temperature drops again. So if you want your pot to boil as fast as possible, leave the lid on so the escaping molecules can't get away. Then the temperature will rise faster. Okay? So a watched pot will boil, it just takes longer, unless you have a glass lid, in which case you can then watch it and still have it boil. Okay? But in the old days, they didn't have glass lids. So the phrase, a watched pot never boils, was a reminder to leave the lid on. Here's another example. If you spray water on your skin, have you ever noticed that it feels cold? In fact, your body is so good that when you start working out and you get hot, your body cools itself by putting water on your skin, which is called sweat. And if there's a thin layer of water on your skin, then some of those water molecules, which are moving fast enough, will escape and leave behind cooler water. Okay? You may notice when you get out of the shower in the wintertime, you feel really cold. That's because of evaporation. The water layer on your skin is leaving and leaving your body colder. Okay? If there's lots and lots and lots of water molecules in the air, then in general, for everyone that leaves, one gets smacked into your body and adds energy. So on a very humid day, like in the summertime when it's humid, and we say it's sticky, we say it's sticky because your sweat doesn't leave your body. There's so much water in the air already that every molecule that leaves your skin, another one smacks in and joins your skin. And you don't cool when it's humid, okay? So that's an example of evaporation. So evaporation is a special process. We're not really going to worry about it mathematically or anything. Just kind of wanted to talk about it in that context. All right, so here's the big graph that summarizes everything we're going to do this unit. By the way, this is the last. Uh-oh. Can you guys see my graph there online? Andrew? You see a graph?
Yeah.
All right. You guys missed all the slides on evaporation because nobody told me I forgot to share it. There's the slide you missed. All right, so here's the big graph. This summarizes everything in the unit, okay? We've already talked about the fact that when the temperature is changing, the amount of heat is MC delta T. What we are going to add is what happens when we're changing phase, okay? So this graph kind of shows the big picture. All substances, when they're moving slow enough, will be a solid. As they move faster and faster, sooner or later, they will melt and turn into a liquid. Once they're a liquid, as they move faster and faster, they will eventually reach a point where they will begin to boil. This is true for every substance. It's true for oxygen, it's true for metals, it's true for water, okay? And eventually when it's done boiling, it turns into a gas, and then adding energy causes the temperature to change. So we made little temperature versus heat diagrams, and we drew little arrows that look like this, right? What we're going to add today is what happens when we change phase. All right? So there's a couple things we have to know. We have to know at what temperature does this happen, and how much energy does it take to change the phase from a liquid to a gas, for example. Now, think about oxygen. How do you guys know oxygen? Is a solid, a liquid, or a gas? Oxygen's a gas. The reason is the bonds, the attraction between oxygen molecules is pretty darn weak. And at room temperature, they're moving fast enough to stay apart from each other. But iron, the attraction between the molecules is very strong. So at room temperature, they have the same velocity as oxygen, the same energy, but that energy is not enough to rip them apart, okay? So they're stronger bonds, so they're still stuck together at room temperature. You've got to heat iron really hot to get it to melt, okay? So whether something's a solid, a liquid, or a gas at room temperature just depends on how strong the bonds are. Here's a conceptual question from the test. Compared to iron, at room temperature, the bonds for oxygen are stronger, weaker, or the same strength. Compared to iron, how are the bonds between water molecules at room temperature? Are they stronger, weaker, or the same strength? They're weaker. They're not strong enough to hold oxygen together in a solid. You got to really slow oxygen down, hundreds of degrees below zero, before the molecules are moving slow enough for oxygen to form a liquid, okay? All right, now, how much heat does it take to change the phase of an object or a substance? Well, that just depends on the mass, okay? So add this to your toolbox. When we are changing the phase of a substance, the amount of heat it takes is the mass times a constant called the latent heat. And again, we're going to look this up on a table. So Q equals M times L tells you how much heat you need to change the phase. M times L. M is the mass, L is a constant we're going to look up in a table. Don't worry about the different things down here. I'll talk about those in a second. So you may have noticed when you guys were looking at the tables during the homework, right? There were 3 tables. The first one was about how much things expand. The second one was about the heat capacities. The third one looked like this. And this is the last table we're going to use. Okay? For a couple of different substances, it tells you the temperature. Is that our stretch break? Everybody take a quick stretch. It's stretch time. Come on, stretch, stand up. Come on, Reagan. David's not going to do it. He's a slow-moving molecule. All right, if you are getting tired of sitting and you want to stand up during this, just make sure you're not blocking anybody's view behind you and stand up. It doesn't bother me at all. All right, so this big table tells you everything you need to know about a couple of different substances. Water, for example. The first thing in the table, let me get a highlighter here. Okay, so for water, the first column tells you the melting point. This is the temperature at which it turns from a solid to a liquid. It's 0 degrees Celsius. You already knew that. The second thing tells you how much energy you need to change it from a solid to a liquid. 3.33 times 10 to the fifth means 333,000 joules of energy are needed for every kilogram of water. So this thing right here tells you, look at the units at the table. It tells you how much energy is needed per kilogram. Okay? The next thing it tells you is at what point does it start boiling? That's 100 degrees for water. And then it tells you how much energy you need to convert a kilogram of water from a liquid into a gas, which is 2.26 million joules. You need a lot of energy. Okay? All right, so let's practice reading the table. You guys at home there, pay attention. I'm going to call on you too. All right, at what temperature does ethyl alcohol boil? Turn from a liquid to a gas. Maggie? 78 degrees Celsius, that's right. Yep. Okay, Maggie, at what temperature does ethyl alcohol turn from a gas into a liquid? Gotcha. At what temperature does it turn from a liquid to a gas? At 78. At what temperature does it turn from a gas back to a liquid? At 78. Okay, that's the temperature it changes from a liquid to a gas or a gas to the liquid. Okay? All right, let's see. Garrett, how much energy does it take to turn a kilogram of silver from a solid into a liquid? We're looking at silver. We're going to go from a solid to a liquid. How much energy will it take for each kilogram?
8.82 e to the fourth.
That's it. You got it. So this number right here tells you how much energy you got to add to convert a kilogram of silver from a solid to a liquid. All right. How much energy do you have to remove to take a kilogram of silver from a liquid back to a solid? Naomi? Yep, same answer. She's saying it quietly so you guys at home can't hear. Same thing. So if we're going to convert from a liquid to a solid, we got to take this much energy away. If we're going to convert from a solid to a liquid, we got to add that much energy. Okay? All right. So if we're going from a solid to a liquid, we are going to use the latent heat of fusion. That is this first column. If you're going from a liquid to a solid or a solid to a liquid, we use the latent heat of fusion. And if you're going from solid to liquid, you make it positive. And if you're going from a liquid down to a solid, you're removing energy. You make it negative. Does that make sense? All right. If you're going from a liquid to a gas, you're boiling or you are vaporizing. So we use LV. So that is the last column, the latent heat of vaporization. This is what you use when you're going from a liquid to a gas or from a gas to a liquid. If you're going from a liquid to a gas, it's positive, you're adding energy. And if you're going from a gas to a liquid, you are removing energy. Okay? You good? So when we solve a problem, guys, we're going to make this diagram every time. If your problem involves changing temperatures, we were already doing this, right? I told you how to make a diagram of Q versus T. If you're changing phases, your diagram is going to look like this too. And what I want you to do now is pretty carefully think about what part of the diagram you're doing, okay? So if I had water and all I was doing was boiling it, I would be on this section of the diagram right here. Here, right here, we have water at 100 degrees as a liquid. And as I move from there to here, I'm adding heat. Q is getting bigger, right? The x-axis. But Y, the temperature is not changing. That's why it's horizontal. So what's happening from here to here? I'm turning my liquid into a gas. Okay? If I were to just melt something, I would be going from here. So this is solid at its melting temperature. If I add heat, it will turn into a liquid at its melting temperature. I go from there to there. Okay? And if I were to melt something and then warm it up, going from here to here is melting it, and then I might go up to there. That's warming it up. Okay? So, here's an example problem. How much heat would you need to completely melt 0.25 kilograms of ice that starts at 0 degrees? If I just want to melt the ice, how much heat will I need to add? Okay, well, here's what my diagram is going to look like. Right there. I'm going to draw an arrow on the section of the curve that represents melting. Okay, so you're going to draw this curve. Make it a little dotted line, and then highlight. Use a highlighter, use a different color, use a bold line, I don't care. Highlight the section that is represented in the problem. So if all we are doing is melting an ice cube, we are going from right here to right there. Okay? Now, to find out how much energy that is, we've got to figure out what we're doing. Well, since it's water, ice is water, we're going to use this value for L. 3.33 times 10 to the 5th. So to find out how much energy we need, we just take M times L. So grab your calculator. Take the mass of the water, 0.25 kilograms, and multiply it by the amount of energy you need for every kilogram. So times 3.33 e to the 5th. And what do you think, Gabby? What'd you get? She's going to pass. Reagan, did you get it? The mass is 0.25 times 3.3 e to the 5th. Got an answer there? Yeah, 83,000 joules is how much energy it takes to melt an ice cube. So it started at 0 degrees as a solid. It ended at 0 degrees as a liquid. It took 83,000 joules. In a microwave that was 1,000 watts, that would take 83 seconds to melt that ice cube. Okay? Because it adds 1,000 joules every second. All right, that's example 1. That's half your problem. They're just like that. They're pretty easy. Here's a slightly more complicated problem. What if I have a small ice cube? So I grab one of my ice cubes at home. It's 25 grams. Okay? And I want to start at 0 degrees. I want to completely melt it, and I want to warm it up to 22 degrees. So take a second and see if you can sketch what parts of the heating curve we're going to trace. It starts off as a solid at 0 degrees. 0 degrees is its melting point. So where does it start off on the heating curve? And where does it end up? And this is the most difficult part of these problems. Once you figure this out, doing the calculation is easy. So what you're going to do in your homework book is you're going to draw this diagram that I have here in blue on each problem where you got to make a solution. And then you're going to highlight the section that we're interested in. So down here, it's a solid. The first green line is the melting point. And since the melting point is 0, we're starting right here at this spot. So we're going to go from there to there. That melts the ice. Are we done? No. We're going to warm it up. We're going to warm it up to 22 degrees. So these are the two sections of the heating curve that we're interested in. Now remember, when it is flat, when the temperature is not changing, you find the heat using M times L. When it's changing temperature, you use MC delta T. That's what we've already done. So here's my variable list. Because I am melting ice, I use the table for the latent heat of fusion for water. And then once it's melted, I have liquid water. So the heat capacity, when I use MC delta T, C is going to be 4,186. Okay? So my solution is going to look like this. The heat it takes to do this is going to be M times L. That's this horizontal section. Plus MC delta T. And you know all those things. M is the mass. L is the heat of fusion. That 3.33 e to the 5th. M is the mass. C is the heat capacity. And delta T is how much the temperature changes on this second segment. It goes from 0 to 22. You can find the temperature change. So you plug in all your numbers, and it turns out to be about 10,600 joules. Now, this is a pretty small ice cube, so that's not a terrible amount of energy. Okay? You see how to do that? So that's what we're going to practice. All right? That's going to be the homework, solving those kinds of problems. The first couple problems in your assignment, you don't need to show any solutions. I just ask you questions about the table. Just answer them. When you get down there where it says start showing solutions, I want you to draw this curve, do it in dotted lines, and then highlight the section that you're interested in, and then do the calculation. All right? Does that make sense? All right. So you guys got half an hour to solve the problems. If you are online, you can disconnect. I'm going to start recording, and you can come back if you have any questions. See if you can work through and do those problems in problem set 7.5. And this is the end of the unit, guys. Tomorrow we'll talk about some concepts, then we'll review and have a test. So we're winding down. Okay? All right, I'm going to stop the recording.